We're going to move into numbers 10 through 18. Let's just keep on going. For 0 to pi over 2, the antiderivative of 2 tangent x. When I see the antiderivative of this, there is a way to just, well, we could just memorize it, but there's a way to do it without having to memorize it. We're taking the integral. This is the antiderivative. So we're going from 0 to pi over 2. And we have 2 tangent x. Well, tangent is really equal to sine of x over cosine of x dx. And then we can pull this 2 out front. Now I notice down here that I have a u, and this is like a u prime, but it needs a negative. So I'm going to put a negative there and balance it with a negative in front. And the antiderivative, or the integral of u prime over u, is natural log of u. So this means that I'm going to have negative 2 times natural log of cosine of x evaluated, or what are we looking for here? Negative 2 times natural log of cosine of x. That's it. So now you're probably thinking, wait a second. So how do I make that look like one of these here? Well, a lot of it has to do with this number and using it as a power up here. That means that we're going to have negative natural log of cosine of x to the negative 2 power. Negative 2 power means natural log of 1 over cosine squared x. And 1 over cosine is really secant. So this is natural log of secant squared x. Now it looks like one of these answers. So we got to realize that that power out front, the power rule for algebra with logs, allows us to take this to this to this. Alright, next. If the substitution u equals x squared plus 1 is made, then we have this. This is going to be our key. U equals x squared plus 1. We're going to derive everything from that. If we know that u equals x squared plus 1, then we also want to figure out what x equals. And we also want to figure out what dx equals. So if I did du equals 2x dx, then that means du over 2, or 1/2 du, equals x dx. I also know if I were to solve this, I'd have u minus 1, and then we'd have the square root equals x. So that's another way of thinking about this. So let's see how this would all fit together. Another way of thinking about this is just u minus 1 equals x squared. So if I have the integral, the first pieces are going to be translated as 2 and 0. Well, actually, I could, even before that, just put this u on the bottom. U equals x squared plus 1. So that piece is here and goes here. For the boundaries, if x equals 2 and u is that squared plus 1, 2 squared plus 1 is 5. If x equals 0, 0 squared plus 1 is 1. So it automatically cancels out b as a choice and e. Dx is going to be du over 2x, or x dx. So right now I have x cubed dx. Well, if I multiply, let's see what we got here. This x cubed, this would actually be an x squared and an x. I could break that up. So then the x dx is going to be 1/2 du. And the x squared, we'll do that in orange, the x squared is u minus 1. So we've got to somehow put all of this together. Well, the boundaries, nothing really changes with those. This 1/2 can become a 2 on the bottom. And we have u minus 1 up top and du. Let's see if something matches that. Looks like it's going to be A. Because we have the 2 on the bottom, the u minus 1 on top, and the u here. There we go. Next. The equational line tangent to the curve, blah, 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 is, add x equals 2, is this. What's the value of k? Well, if I know that y equals kx plus 8, whenever I have a constant, I usually have to do whatever type of calculus operation it's asking me to do or is implying for me to do. It's this tangent line. That means I need to find derivative over k plus x. That means that y prime is going to be, this is a quotient rule, so I have low d high minus high d low. Square the bottom and off you go. Low, low. Let's take that back, make it a little bit cleaner. Let's make it really clean. There we go. So let's start with the low d high. That's going to be k plus x. Oh, by the way, this is an 8. K plus x times the derivative of the top. Well, the 8 goes to 0, and this kx just goes to k. Minus, let's do high d low. Well, that's kx plus 8 times k. Then on the bottom we're going to have k plus x. That's going to be squared. Clearly, I could probably simplify a bunch of this stuff because I got k plus x and k's and all kinds of stuff all over the place. Let's see what would happen. Well, we have y prime equals, let's put this back in black, y prime equals, if I were to multiply this first one out, that means I have k squared plus kx. If I multiply the second one out, I'm going to have minus kx, k squared x, and we got minus 8k all over k plus x squared. Now as I'm looking at this, there's a couple of things I know. First, I know that x equals negative 2, so I could replace that. Second, I know that the slope equals 1. So on the left side here, I'm going to have a 1. This is the slope. This is what it's supposed to simplify down to. On the right side, I can plug in negative 2 for x and then figure out what k is. That means I'll have k squared plus negative 2k, if I plug in an x there, plus 2k squared minus 8k all over k minus 2 squared. Again, this is just a bunch of algebra. On the bottom, we'll have k squared minus 4k plus 4. And on top, we'll have 3k squared plus, or minus, I should say, minus 10k. That equals 1. Well, if I multiply both sides by k squared minus 4k plus 4, that gives me k squared minus 4k plus 4 equals 3k squared minus 10k. Now I can start combining like terms across the equation sign. So if I subtract k squared on both sides, I'll have 2k squared over here. If I add 4k to both sides, I will have minus 6k. And if I subtract this 4 over to the right side, I'm going to have minus 4. I got that equal to 0. Why am I doing this? Because whenever I'm done with a quadratic type function where it's to the second power, I want to be able to factor, quadratic formula, something like that, and noticing what these values equal here, that means that I probably can factor this. Well, let's pull out the 2, then we have k squared minus 3k minus 2. I can factor that. So it's got k minus 2 and k minus 1 times 2 equals 0. Well, here's something that's interesting, because if you look at that, k would either equal 2 or 1. Well, k can't equal 2 for a couple of reasons. One, it's not on the multiple choices, but 2, right here, the denominator cannot equal 0. That would make the denominator equal 0. It would just kind of throw everything off. But it can equal 1. So k does equal 1. It was that simple. So much algebra just for one simple process here. The function f is continuous on the closed interval and differentiable on the open interval. Blah 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 blah. Oh, use subintervals. So we got 5 to 6, 6 to 9, 9 to 11, and 11 to 12, and a right-hand sum. So how many boxes I got here? I got 1, 2, 3, 4. So I need to make 4 boxes. Because we're doing Riemann sum, we're going to be adding them together. Well, the first interval goes from 5 to 6. So how wide is that? It starts at 5, it goes to 6, so it's just 1 wide. It looks like I made it a little bit wider than it actually was. Next one goes from 6 to 9, so the width of that one is going to be 3. Then we got 9 to 11, so that width is 2. And 11 to 12, so that width is again back to 1. Now I need to figure out the height of each of these. Well, the height for the first one comes from the height equals f of 6. How do I know that? Because I got to choose the right side for the first box. So the height of this one is going to be 7. The height of this next box is going to be 11. The height of it, following the same type of pattern, the height of the next box after that, from 9 to 11, is going to be 12. And the height of the last box is going to be 8. So all I really need to do now is find the area of each box and add it up together. So we got 8 times 1 is 8, 12 times 2 is 24, 11 times 3 is 33, 7 times 1 is 7. Okay, so we got 40 plus 32, that equals 72. It was that easy. Because this piece here equals 40, 24 plus 8 is 32, add them together, we get 72, done. You guys are doing great, keep on hanging in there. Alright, for this one, I especially have an appreciation for being able to visualize what's going on. First it says we have a vertical asymptote at x equals 2. So I have a graph. It's got an x-axis, it's got a y-axis, but then at x equals 2, about here, whoops, not out there, at x equals positive 2. Let's see out here. There's a vertical asymptote. So let's see what's happening in each of these. It says the derivative is positive. That, another way of interpreting that is meaning that the slopes are positive. And even further, the function f is increasing. Okay, so f is increasing on this interval. Well, let's see what happens with these three options and see how they agree with that statement or disagree. The first one says limit as x approaches 2 of f of x is going to infinity. Now notice that there's no left or right. That means the limit as it's coming from the left, it's going to positive infinity. The limit as it's coming from the right, it's going to positive infinity at x equals 2. So that's the first one. The second one I'll do here in green, number 2, is saying the limit as it comes from the right. So number 1 says both sides it goes to infinity. Number 2 says that it's just the right side. It's the right side. The limit as x approaches 2 from the right. From the right. That's going off to positive infinity. Well, let's see what happens after that one. The next one says, number 3 here, is saying the limit as x approaches 2 from the left is also positive infinity. That means that we have from the left side it's going to positive infinity. Let's see which of these 3, if all of them or only one of them or some of them, follow these same things that we started, some of these same guidelines. The slopes are positive, which means it's increasing. Well, in number 1 here, I see this second half of it's not increasing, so 1 is out. Similarly, in number 2, even though it's saying it's going to positive infinity as we go from x from left to right, it's decreasing. So that means that 2 is out. And the only possible option is 3. And it is true on this one because we are increasing. We're not decreasing, we're increasing. In numbers 1 and 2, we each had a section that was decreasing. But it says it's positive for all x not equal to 2. Therefore, it should be increasing the entire time. That wasn't too bad. Okay, let's try this one. There's a formula that you can memorize for this, but whenever I see something that has a power with a function in the power, I like to use logs, because logs allow us to take that power down. Because remember, if we have log, or natural log, let's say, of b to the a, that's really a times natural log of b. So let's apply that here. We have y equals 5 times x cubed minus 2. If I take the natural log of both sides, let's take those back and color them a little bit differently. If I take the natural log of both sides, that means I'll have natural log of y equals natural log of 5 times x cubed minus 2. And I can pull this power down, so it's going to be equal to x cubed minus 2 times natural log of 5, which is really just a constant, so that doesn't really affect us too much when we take the derivative. The constant just kind of carries through. So I'm past this middle stage. Now I'm going to just deal with the right side and left side here. I'm going to take the derivative of both sides, dy or d dx. That's what I want to do. d dx. Why? Because I want to take the derivative with respect to x, both sides. d dx. We'll do that in a different color too. d dx. d dx. Okay, what's the derivative of natural log of y with respect to x? Well, first of all, the derivative of natural log of anything is going to be dy over y, or we could just say 1 over y dy dx equals. And then on the other side, that natural log of 5 is going to just sit there. We don't have to really deal with it. The constant multiple rule allows us to just kind of attach it to the derivative and ignore it for now. And then the derivative of this other piece, x cubed minus 2. Well, this is kind of weird because when you multiply the natural log of 5 in there, this natural log of 5 times the 2, that's going to be a constant. So we got x cubed times natural log of 5. We got minus 2 times natural log of 5. This piece here, that's a constant, so that disappears when we take the derivative. We're just worried about the other piece there. So we have natural log of 5 times the derivative of x cubed, which is 3x squared. We keep on going from here. I'm going to multiply both sides by y. Why would I do that? Because I want dy dx. I want to solve for dy dx, so I want the y gone. Then I have dy dx equals y times natural log of 5 times 3x squared. Well, y was originally 5 to the x cubed minus 2. So it's going to be 5 to the x cubed minus 2 times natural log of 5 times 3x squared. Let's see what matches. Looks like this one. B for bingo. Or Butler. Ooh, The graph is given. This graph is, these are derivatives, these are slopes. So that means if I'm above x, that means my slope is positive. And if I'm below the x-axis, my slope is negative. One way to think about that is I'm increasing when I'm up here and I'm decreasing when I'm down here. When I'm at 0, I'm flat. So let's interpret that. So when I'm down here, I'm going to color these parts below the axis, well, just this one part in red. And then above the axis, let's color that in blue. So that means for the blue area, I should have increasing or positive slope. For the red area, I should have decreasing or negative slope. And there's one key point here where I actually have decreasing, then flat, then increasing slope, which means I'm going to have a min. There's another point here where I'm increasing, then I'm flat, and then I'm increasing again, so I'm going to have a point of inflection there. So let's see where I have that. At -2, I have a min. Well, that would easily cancel out C and B and even A. And I think there's an answer further down here. Let's see if it's down there. So that means I can probably erase these marks. So it's between D and E. Which one do you guys think it is? I hope you guessed D. The answer is D, because notice that I have a min at about -2. I have a point of inflection about here. I have decreasing slopes up to -2, but then after that I have increasing, then flat, then increasing. So D would have been the correct answer. Ooh, this one's different, because you notice that we have the derivative of the integral, which normally onto each other, especially when we have a constant and x. But this is kind of backwards. Normally we're used to seeing it as 0 to x, like this. Well, this is actually equal to the derivative of negative integral from 0 to x du over 1 plus u squared, because the integral from a to b of f is equal to negative the integral from b to a of f. We can flip the boundaries and make it negative. Let's see how that affects us here. Remember, the derivative of the integral, those pieces are going to cancel each other out, and then we're really looking for plugging in the top times derivative of the top, plugging in the bottom times derivative of the bottom. So we're going to have 1 over 1 plus x squared times the derivative of x, which is just 1, minus 1 over 1 plus 1 squared times the derivative of 1 plus 0 squared times the derivative of 0, which is 0. So that second term goes to 0. We're just interested in the first term. Now, you think that we'd have the answer, but we forgot this negative. So that should be negative. The actual answer should be negative 1 over 1 plus x squared. Do we have that? Well, b would be our closest friend here, because 1 plus x squared is the same thing as x squared plus 1. So that's our answer. Ooh, the last third of the non-calculator. We're so close to the finish. Let's accelerate. Let f of x be differential function defined only on the interval -2 to 10. The table below gives values of f of x and the derivative f prime of x at several points in the domain. The line tangent to the graph and parallel to the segment between endpoints that intersects the y-axis. Let's see if we're missing some words here. I feel like there's something there. The line tangent to the graph of x and parallel between the endpoints. Okay, well then let's talk about these endpoints. We got these endpoints here. So what's the slope between those two endpoints? Well, the slope between any 2 points, if we were to look at these kind of pairs here, is going to be, this is the average slope, by the way, because it's from the beginning to the end. So the average slope is equal to the difference in the y's over the difference in the x's and the second y here is going to be 2 minus 26 over 10 minus negative 2. Well, if I put those two pieces together, I get negative 24 on top and 12 on bottom. That reduces down to just negative 2. So my slope equals negative 2. So it's tangent to the graph f prime of x and parallel to the segment between the endpoints. So I need to find something parallel to negative 2. That means it has a slope equals negative 2. Or a tangent slope, I should say. Tangent slope equals negative 2. What does that mean in terms of calculus and algebra and equations and stuff? That means f prime of x equals negative 2. So f prime of x equals negative 2 means I need to figure out when or what is x. Why do I need to know that? Because it's asking me to find the y-intercept. But I can't even find the y-intercept if I don't know my equation. Because my equation is going to be y equals mx plus b. Well, I know m, that's negative 2. I need to figure out x and y and then find b. Well, let's see what we got. M equals negative 2. X, which one of these gives me negative 2? Aha! Here it is. M equals negative 2. X equals 4. Y equals 23. So let's plug those pieces in and see what we get. We got 23 equals mx plus b, so we have y equals mx plus b. The slope is negative 2. X is 4 plus b. So this is going to be negative 8 plus b is 23. Add 8 to both sides. 27 equals our y-intercept. Oh, that wasn't too bad. That's kind of long. Pretty simple. We could have even solved that with just a geometry student. Next, at each point on a certain curve, the slope of the curve is 4xy. What does that mean? That means that dy dx equals 4xy. If the curve contains the point 0, 4, that's an x and a y coordinate, then the equation is. Well, let's see what we get. I have a feeling it's probably going to be this one, or this one, or this one. I don't know, but I'm almost guaranteeing it's not going to be d or e. How do I know? Because it has a y in my derivative here. So first I need to do separation of variables. If I separate these variables, I get the y with the dy and the dx with the x. Then it's going to make it a little bit easier to integrate. So I have dy over y, if I move the y over here, equals 4x dx. If I integrate both sides, that'll give me natural log of y on this side. Equals, on the other side, I'm going to have x squared over 2 times 4, which is just going to be 2x squared, plus c. Now, in order to simplify this even more, I need to raise both sides with a base e. Now, from other ones, we know that e to the a plus b is really e to the a times e to the b, which is really e to the a times b, because b is a constant, and so is c. So this e and natural log, those reduce, and we're just left with e, or not e, we're just left with y equals. On the other sides, though, this c is going to pop out front, so we're going to have c times e to the 2x squared. Here's where our other information starts to come into play. We know that x1 is 0, or x is 0, and y is 4. So we're going to plug those in. That means that 0, no, this is 4, that's my y value, equals c times e to the 2 times 0 squared. That's my x value. Well, if I were to simplify these things, e to the 2 to the 0, 2 times 0 squared is going to be e to the 0, which is just 1. So 4 equals c. Well, the only one that even comes close to that is going to be this one right here. That was easy enough. A few more to go here. The equation of